Hi. In this video, we're going to go through a few worked examples using the LU decomposition to solve linear systems. In the first example, let's start with how we can solve a linear system, AX equals B, when we are given the LU decomposition of that system. We're given L, U, and a right-hand side B for a simple LU decomposition that does not involve row exchanges. I recommend that you pause the video here, try to solve the system, and then resume to follow the worked solution. The first step in solving systems by LU decomposition is, after LU decomposition itself, is to set up two triangular systems that represent the original system. We can I'll remind you of the conceptual process behind that. If we have some AX equals B, and A can be written as LU, then we can replace A with LU. That gives LUX equals B. If we isolate the U and the X, the UX can be replaced with C. And this gives us a pair of equations, LC equals B and UX equals C. Right? Where L and U, because of their structure, are easy to solve, as we'll see in a moment. Given two systems then, an LC equals B, where we have our L matrix, a given B, and an unknown C, this problem can be solved for C. UX equals C, our U matrix, our unknown vector X. Initially, we have an unknown vector C, but after solving the first system, we can substitute the numbers that we get for C here, and then solve for X. A two-step process, first solving the lower triangular system, and then the upper triangular system. So, first step, go through and solve the lower triangular system. Just sort of to remind what our original system is. How do we solve this sort of system? Well, we know how to solve linear systems. We can form an augmented matrix where the first block is L and the last column is B, and then go through Gaussian elimination to solve. Because we're starting with a lower triangular matrix, Gaussian elimination is going to be very straightforward. We use our pivot to eliminate downward. The pivot variable will always be 1 because of the structure of L. Subtract 1 minus the second row minus the first row gives us 0. Because of the extra zeros here, the rest of the row is easy. 1 minus 0, 0 minus 0. And for the right-hand side, 5 minus 2 gives us 3. To eliminate the 2, we subtract 2 times the first row. 2 minus 2 is of course 0. Again, because there's zeros in this row, a half minus 0, 1 minus 0, they're unchanged. And 3 minus 2 times the first row, so 3 minus 4 gives us -1. We then move over and down. Our next pivot, again, it's 1, so the factor is easy. We're going to add half of the second row to eliminate the third. Half minus half is obviously 0. Again, because we have zeros here, the next entry is unchanged. And half of 3, that's 3 halves, minus 1 gives us 1/2 for the last entry. So we now have a block with I, and our right-hand side, which becomes our C vector. Notice that we only had to take forward elimination steps here. We did not have to do back substitution because we started out with a lower triangular form. We already have zeros above the diagonal. Our pivots are already all 1, so it's a very straightforward problem. This is exactly what we mean when we say the triangular systems are much easier to solve than a typical matrix through Gaussian elimination. So very quickly find C. Once we have C, we are now ready to solve for the upper triangular system. We've used the C value that we just calculated, our matrix U from before, and we take exactly the same approach. We set up an augmented matrix where the first block is U, where the last column is our vector C, and we wish to solve this. Again, we take Gaussian elimination. Because U has already stored the steps of forward elimination, it's already in an echelon form with our pivots here. The only thing we need to do is back substitution. We start with the back substitution piece. We might note here that this system has 3 pivots, but also a free variable. We expect this system to give us multiple solutions. So, carrying through with back substitution, we start at the bottom, the last pivot. We first scale this entry by multiplying by 2 over 5. This gives us 1 negative 1/5. We then use this scaled entry to eliminate upwards, adding the third row to the second. Negative 1 plus 1 is 0. 3 minus 1/5 is 14/5. And we subtract 4 times the third row from the first. 4 minus 4 is, of course, 0. And 2 minus negative 4/5 also actually happens to give us 14/5. We then move up and over. Here we actually jump over 2 columns to our next pivot because we had a free variable. And scale by dividing everything through by negative 2 gives us 1 and negative 7/5. And then eliminate upwards with this pivot in the second row. We do this by subtracting 3 times the second row from the first. 3 minus 1 is, of course, 0. 4 minus 0 is 4. These are zeros, so we ignore them. 14/5 minus 3 times negative 7/5 is 14/5 plus 21/5. 35/5, which is 7. Move up and over to our last uppermost leftmost pivot, and the only thing left to do is to scale dividing by 2 to give us our final system in reduced row echelon form where every pivot is 1 and in an isolated in its column as the only non-zero entry. Right? Again, free variable in the third column. Since we're now in a reduced row echelon form, we are ready to solve. The system has multiple solutions. We translate the augmented matrix back into a system of equations. x1 plus 2x3 equals 7/2. The non-zero free variable coefficient in the first equation. The second and third equations have zeros in the free variable position, which means these get simply written as x2 equals negative 7/5, and sorry, it should be x4 equals negative 1/5. Right? We can then rearrange to isolate the pivot variables all on one side and the free variables on the other, and then write this in a parametric form of x1, x2, x3, x4 is 7 halves minus 2t minus 7 fifths, t, and negative 1 over 5, where t can take on any number. We can solve a system by breaking down the problem into these two lower and upper triangular systems. Okay, let's go through another example, one that's a little bit more complicated because we're going to add in the row exchange piece. Can we solve, again, a linear system, ax equals b, where instead of being given A, we are given the LU decomposition with row exchanges. We're given PA equals LU with a P matrix, a permutation matrix, a lower triangular matrix, an upper triangular matrix, and our right-hand side. Again, I recommend that you pause the video, try to solve it on your own, and then resume to watch the solved solution. Okay. The first step in this process has to be applying the row swaps to the right-hand side. Similar to the last problem, we're going to sort of start with our ax equals b and our sort of encoding of A as an LU decomposition. And note that we have a P here, which means the very first thing we would need to do is to write both sides, multiply both sides by P. After doing that, we can recognize that PA can be replaced with LU, and this gives us LUX equals PB. Right? We can write PB as B prime. That gives us one equation. We can sort of set a temporary variable of C to be equal to UX. That gives us our UX equals C equation, and LC equals B prime is the piece that we're left with in the middle. We have three equations to solve, and we actually are going to want to solve them in this order. First of all, find B prime using our permutation matrix, solve for C using B prime, then solve for X using C. It might look like this is more complicated because we're requiring 3 steps instead of just one step of Gaussian elimination, but each one of these steps is an easier problem, a much easier problem. Okay. Start with the first piece. Apply the row swaps to the right-hand side. We simply multiply our given right-hand side by our permutation matrix. We can either do this by just applying rules of multiplication. The first row with all zeros except for a 1 in the second column pulls out the second entry, so we get a 0. The second row with a 1 in the first column and zeros everywhere else pulls out the first entry, so it becomes a 1. The third row pulls out the last entry, a -1, and the fourth row pulls out the third entry of a 2. We also could look at this. This system was the system that we worked through in the previous worked example video. Involves a row swap of row 1 and row 2. That's what these two sort of pieces represent here. And these two pieces where the ones are not on the diagonal represent exchange of row 3 and row 4. Instead of multiplying the matrix, if we know that these are the row exchanges, we could simply do that. We exchange rows 1 and 2 and exchange rows 3 and 4 to get our B prime that we're going to use to move forward. Once we've found B prime, we can now move on to our second step, solving the lower triangular system. Right? Just to be clear where we're going, the two triangular systems that we're going to be solving, I've now put in B prime here. Sometimes you will just see this written as LC equals P times B. Our lower triangular matrix, our row swapped right-hand side, we're going to solve this for C. Once we solve for C, we can plug that into our upper triangular form. Okay, moving forward with the lower triangular case. Our lower triangular matrix, our row swapped right-hand side. Exactly the same process as we've seen before. Encode this in a augmented matrix with L and B and go through Gaussian elimination. Because we're in lower triangular form, we will only need forward elimination steps, and those steps will be easy. Second row already has a 0. Subtract the first row from the third, because the only non-zero entry of the first row is a 1. That just puts a 0 here, and everything else is unchanged. Subtract half times the first row from the fourth. Again, because there's zeros everywhere else in the first row, this just creates a 0 in the first position of the fourth row, and everything else is unchanged. We now move down to the next piece here. I'm supposed to emphasize we didn't have to do anything in the right-hand sides here because we were starting off with a 0 here. We now move over and down, another pivot, eliminate downwards. To eliminate this -2, we add twice the second row to the third. That gives us a 0 in the pivot position of row 3. Zeros in the third and fourth column, so those are unchanged, but a non-zero in the right-hand side, so we have to do -1 plus 2 times 1 gives us 1, our new third row. And we don't have to do anything with our fourth column because we already have, fourth row, because we already have a 0 here. In this case, because not only did we have a lower triangular system, we had a lower triangular system that had row swaps and then thus had a bunch of zeros below the diagonal. There's even less steps than usual for forward elimination, and we find after this second round, we are already in our reduced row echelon form. We have an identity matrix in our coefficient block, which means the right-hand side is the last column is our answer, our C vector. Now that we have the C, we can plug that in to the second system, the upper triangular system, and solve. So here's our C that we just solved for, our upper triangular form that we mentioned before, and we solve in the same way. Augmented matrix with U and C. Note that this is already an upper triangular form. Pivots on the diagonal. There's 4 of them, so this means we have a unique solution. No free variables. We start with back substitution. First entry here, bottom row pivot is already a 1. There's no scaling that needs to be done. So we just use this to eliminate upwards. We add twice the second row from the third row. -2 plus 2 is 0. 1 plus 4 is 5. We subtract the fourth row from the second row. 1 minus 1 is 0. 1 minus 2 is -1. We subtract 4 times the fourth row from the first row. 4 minus 4 is 0. 0 minus 8 is -8. We then move up a row over a column to our next pivot. First step, scale, divide through by -2, gives us 1 and -5/2, and then use this to eliminate upwards. We already have a 0 in the row above, so the only elimination we need to do is subtracting 4 times the third row from the first. 4 minus 4 is 0. 8 minus 4 times 5/2 is 8, or -5/2 is 8 plus 10, which is 2. We've eliminated that, so again we move up a row over a column to our next pivot. Already scaled, already has a 1, so we don't have the scaling step. We just eliminate upwards, subtract 2 times the second row from the first. 2 minus 1 is, of course, 0. And 4 minus 2 times, 2 minus 2 times -1 is 2 plus 2, or 4. Move up and over to our next pivot. Only remaining thing to do is to scale. We have now reached our reduced row echelon form. Every pivot is 1. Every pivot is isolated in its own column. This is the identity matrix, which means this last column is our solution. Right? So we directly move from just reading out the last column as our unique solution to this system. Okay. Now let's try one example where we put all of the things that we've discussed here together. Solve a system presented as a non-LU decomposed system of equations with 2 different right-hand sides, and we wish to solve this for the different right-hand sides using LU decomposition. We will note as we go through that this ends up being a system that we need to use LU decomposition. It is not one that is amenable to solution, for example, by the matrix inverse. Okay. I recommend that you pause the video, make an effort to solve the problem on your own, and then resume to watch my solution. Okay. The first step in any problem like this is to express everything into matrix form where we can sort of work more simply. So we encode this linear system as AX equals B, where A is our coefficient matrix, which really is as simply defined as simply as walking down each column 2, 2, 1, making sure that we put zeros in the case where we're missing variables. Right? 2, 2, 1, 0, 0, 2, -1, 3, -3, -2, 2, -3, 6, and 4, 6, 0, 3. Right? And we have 2 different right-hand sides, one that is represented by 2, 2, 1, 5, and the other one 2, 4, 2, 3, our vector x of variables. Right? Now that we've represented this in matrix form, the next step is to perform an LU decomposition on A. Right? Very important to remember, when we're working on LU decomposition, we apply this to the coefficient matrix, not to an augmented matrix. The whole point of LU decomposition is that it lets us store something about A that allows us to solve the system for multiple right-hand sides. If we had the right-hand sides built in, that wouldn't work. So we start with A. How do we encode the LU decomposition? We carry through Gaussian elimination, storing the steps in L. A is a 4 by 4 matrix. So L has to match the number of rows of A. It will also be 4 by 4. We initialize it by putting 1s on the diagonal and 0s above the diagonal, and then carry through Gaussian elimination, filling out L as we go along. Start in the upper corner, eliminate downward. We subtract the first row from the second. We're filling in the first column of L. The second row, subtract 1 times the first row, so we put a 1. The third row, we subtract half times the first row. We put a half. For the third entry, we have a 0 here. We don't need to do anything. That's the same as subtracting 0 times the first row. We put a 0. Those are the steps, the coefficients we are going to apply. Then do that. 2 minus 2 is 0. 2 minus 0 is 2. 2 minus negative 2 is 4. And 6 minus 4 is 2 for our second row. 1 minus 1 is 0. Negative minus 1 is 0. Negative 3 minus negative 1 is negative 2. And 0 minus 2 is negative 2 for our third row. And our fourth row is unchanged. We then move over and down. We are now looking in our second column. We are going to be filling out the second column of L. For the third row, we are going to add half of the second row to it to eliminate. This is the same as subtracting negative a half times the first row, so it's a negative half entry in L. And for the fourth row, we are going to need to subtract 3 halves of the second row, so a 3 halves gets put there. Actually doing that, adding half of the second row to the third, negative 1 plus 1 is 0. Negative 2 plus 2 is 0. Negative 2 plus 1 is negative 1. And for our third row, 3 minus 3 is 0. 6 minus 6 is 0. And 3 minus 3 is 0. We end up with a row of all zeros. We have actually at this point reached an upper triangular form. But I am going to highlight one extra step. I have actually repeated the matrix for one important reason. If we were to follow the standard sort of rules of Gaussian elimination, we move over and down to our next pivot. We recognize that this pivot is a 0 and has zeros below. It has a column of zeros, means we don't have to do anything for Gaussian elimination. We still need to encode the fact that we didn't have to do anything. We're working on the third column. So how do we fill out the third column of L? The fourth row. We add 0 times the third row to the fourth. We still put in a 0 here to complete our L matrix. Watch out for these little things where skipping a step in Gaussian elimination means we need to fill in the appropriate entry in our L matrix. Okay. At this point, we have our upper triangular form U, pivot, 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 3 pivots, and 1 free variable. Tells us that this is a system that will have multiple solutions if there is a solution. This also is a system where the coefficient matrix has a set of 0 rows. This is a system where some right-hand sides will not have a solution. Right? Some right-hand sides will have no solution, some will have many solutions. Right? This is why, even though A is square, we wouldn't be able to solve this problem using the matrix inverse. It's a singular matrix. No inverse exists. We still are able to solve this problem for multiple right-hand sides using LU decomposition. This is our matrix U, the end point of Gaussian elimination, and we have stored the results of that elimination in L. Right. Now that we have found L and U, we can represent the system as our pair of triangular systems. This works exactly the same way as we've seen before. We're encoding AX equals B. In this case, I'm saying BI because we have multiple right-hand sides. For each right-hand side, we can implement a pair of triangular systems. A lower triangular system involving our BI and a upper triangular form involving the answer that we get for each of those different right-hand sides. We can write down the problem, set up the two triangular systems once in this way. To solve them, we need to go through the two solution steps separately for each right-hand side. Let's start with B1. All right. We solve the first step, the lower triangular system for our right-hand side B1. How do we do this? We put L in the first block of an augmented matrix, B1 in the second. We then move forward with Gaussian elimination, and it will be straightforward because we already have this lower triangular form with ones on the diagonal. Eliminate downwards. Subtract the first row from the second. 1 minus 1 is 0. These are all 0, so we have 3 columns that are unchanged, and then 2 minus 2 gives us a 0. Subtract half times the first row from the third. Half minus half is 0. These are all 0, so we're left with a negative 2. 1 minus half of 2 is also 0. Right? Third row unchanged because we already had a 0. Move over and to the right, our next pivot, eliminate downward again, add half of the second row to the third, gives us a 0. All of the rest of the entries on the second row are zeros, so everything else is unchanged. For the fourth row, we subtract 3 halves times the second row. Again, because all of the following entries are 0, this just zeroes out that one entry, leaving us in our final form. Pivot, 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 pivot. 4 of them, all with 1s. This is our identity block. Since this is our identity block, this must be our solution, 2, 0, 0, 2. Once we've found this, we can go and move forward to our next piece, the upper triangular form. Okay. How do we do this? We plug in our C, construct an augmented matrix with U and C1, and try to solve. The very first thing we note, remember, we are already in an echelon form, an upper triangular form. That means as soon as we have found our C, we are ready to apply the checkpoint at the end of forward elimination. We have a row that is all zeros in the coefficient block, but a non-zero entry in the right-hand side block. This corresponds to an equation of 0 equals 2, which obviously isn't true. The system is inconsistent. There is no solution for this right-hand side. Okay. Moving to the next right-hand side. Same approach. Solve C2 equals B2. Doing exactly the same thing. Augmented matrix with L and B2 in the last column. Carry through the steps of elimination. eliminating downward. These are the same steps that we just took with the previous right-hand side, but what we do with the last column will be different. So subtracting the first row from the second, 1 minus 1 is 0. These are all zeros, and so the next three entries are unchanged. 4 minus 2 is 2. For the third row, we subtract half times the first row. Half minus half is, of course, 0. 3 zeros, so the next three entries are unchanged. 2 minus 1 is 1. Third row, unchanged, because we already had a 0. Move over and down to our next pivot. Do the same thing. Add half times the second row to the third row. Half plus negative half is 0. 2 zeros, so we skip 2 columns, leave them unchanged. Half of 2 plus 1 is, of course, 2. For our fourth row, we add 3 halves, subtract 3 halves of the second row from the fourth. 3 halves minus 3 halves is 0. 2 zeros means we have 2 unchanged entries. 3 minus 3 halves of 2 is, of course, 3 minus 3, which is 0. Our final answer is sitting here in the last column because we have our identity block, ones on the diagonal, zeros everywhere else. The last column is C2. 2, 2, 2, and 0. Note the 0 here in the last entry is what is going to allow this to actually have a solution for the next piece. Looking at the upper triangular form, we do the same thing. We encode we construct a augmented matrix with U and C2. Because we had this last 0, it means we have a row of all zeros. This isn't a problem. It's just an equation that says 0 equals 0. That's true. Not very informative, but it is true. It doesn't lead us to an inconsistent system. That means we can simply carry through with back substitution in order to find a solution. Note we have 3 pivots and a free variable. The solution we get will be non-unique. We will want a parametric form. So carry through with back substitution. First, we scale the last row, 1 by multiplying by -1. Then we take that lowermost pivot to eliminate upwards, subtract 2 times the third row from the second. 2 minus 2 is 0. 2 minus -4 is 6. Subtract 4 times the third row from the first. 4 minus 4 is 0. 2 minus -8 is 10. We then move up and over to our next entry. This is not a pivot. That's our free variable, so we move over one more time to actually find our pivot. Our pivot is 2. The first step is divide through by 2 to scale, giving us 1, 2, 0, 3. We then can use this pivot to eliminate upwards, but look, there's already a 0 there. There's nothing we need to do. That means we're ready to move up and over again. It's not 1, so we need to scale, divide this whole equation by 1, gives us 1, 0, -1, 0, 5. Sorry, divide through by 2, gives us 1, 0, -1, 0, 5. This is now in a reduced row echelon form. The pivots are all have values of 1. They're all isolated in their columns. We have a free variable column that includes non-zero entries. To get our final solution then, we transform our reduced row echelon form back into a system of equations. x1 minus x3 equals 5. x2 plus 2x3 equals 3, and x4 equals negative 2. The last row is an equation that means 0 equals 0. We can just not bother writing that down. We then isolate the pivots on one side, expressing them in terms of the free variable, which in this case is x3, and we can write this in parametric form, substituting that free variable with another symbol just to sort of make things a little bit clearer. X equals x1, x2, x3, x4, 5 plus t, 3 minus t, t, and negative 2, where t can take on any real number. This gives us our overall solution to the problem. The first right-hand side has no solution. The second right-hand side has many solutions with the parametric form here. Okay. That wraps up the examples I wanted to show. I want to take a moment to just mention an even quicker way that we can solve the last sort of problem when we have multiple right-hand sides. We split the problem in half using LB1 to get us C1, and then solving UC1 to get us X, well, to try to get us our first solution, and then did the same thing with B2 to get C2, and then solving that to get our second solution, if it exists. Just as we can speed up regular Gaussian elimination with multiple right-hand sides by making a bigger augmented matrix, you can do the same thing with the LU decomposed form. So we could have, to save a little bit of work, we could have constructed a augmented matrix with 2 extra columns. And this would have taken us to a form that had an identity matrix, C1 and C2. Right? We then could have noted that we then could sort of form a matrix U with C1 and C2 and take that to form our kind of reduced row echelon form with our solutions, or at least most of the solutions for the 2 different right-hand sides. And this approach allows you to sort of even more speed up the application of the LU decomposition to solving multiple right-hand sides by doing the expensive part of elimination once beforehand. But if you have multiple right-hand sides, after having done that, you can put them all in one block matrix to simplify the arithmetic and to avoid having to repeat steps. If you're not comfortable with this form and would rather separate them out as I worked through in the worked examples, that is a perfectly reasonable approach to take also. If you are comfortable with working in this form, however, it's a little bit of a speed up. Okay, that wraps up our examples of how we can use LU decomposition to solve systems through this pair of triangular systems, each of which are fairly straightforward to solve. In the homework, you'll have more practice with these sorts of problems. Thank you, and goodbye.